Hi everyone, my name is Russell, and welcome to a problem walkthrough from HarkerCTF. In this workshop/walkthrough, we're covering a cryptography problem from ctflearn.com, which is a great resource to practice cybersecurity skills if you're interested in entering competitions or just want to learn more about the field. So the problem that we have here is taken from the CTF Learn website, and as you can probably guess from the name, it has something to do with the RSA encryption algorithm. So here's the problem statement and the link to the problem in case you want to take a look at it. We're provided with a snippet of code that was used to generate some values, as well as the output of that code. And by the end of this workshop/walkthrough, you should have a general idea of how RSA and key generation work and be able to solve this problem. So first, I'm going to talk a little bit about how the RSA algorithm at a very high level works. So RSA belongs to the field of asymmetric cryptography, which is a kind of cryptography that revolves around two keys, a public key and a private key. How it typically works is that the public key can be freely accessible to all parties, while the private key should only be held by people who are to have access to the encrypted information. So let's say that a sender S wants to send a message to a recipient R. S should use R's public key, which is freely available, to encrypt that data, and then R receives that data, and they should be able to decrypt it using the private key that was never shared with anyone. Okay, so far, this kind of system of having a public and a private key seems to make sense. But how are the keys actually generated? So RSA is predicated on the idea that factoring composite numbers that are the product of two primes is hard to do. So let's assume that we have two big prime numbers, and we'll just call them P and Q. In this example, P and Q are taken to be 61 and 53, just to make the problem easily workable. And in this workshop, we won't worry about how exactly these large prime numbers are generated, but there are multiple ways to do that. Then the next step in generating the keys is to multiply the two prime numbers P and Q together to get a composite number, n. And as we discussed earlier, it is very difficult to factorize n. Next, we compute Euler's totient, symbolized by phi, between P and Q, which is just P minus 1 times Q minus 1. And this number is 3,120 in this example. Finally, we're able to find the values of E, which is going to be our public key, and D, which is going to be our private key. So to get E, we can choose any integer that is relatively prime or co-prime with phi. And relatively prime just means that the two numbers don't share any factors except for 1. So in this example, we could choose 17, since the factors of 3,120 don't include 17. But we could have also chosen a bunch of other numbers though, since there are so many different choices for the public key. And then lastly, we want to find D, which is going to be the private key. And I'm going to skip the details of finding D, since it's not very important to this problem, but we do it using something called the extended Euclidean algorithm. And for the purposes of this problem, we can just use a library implementation of that algorithm and not worry about how exactly it works. So this was a very high-level overview of key generation. I glossed over a lot of important details, such as the mathematical machinery which makes this process work, like why is this the way that it's done, and also how the public and private keys are actually applied to the data to encrypt and decrypt it. Those are all really important, but I didn't want to cover them now because they're not very relevant at this point. If you're interested in learning more about the mathematical aspects of RSA and how it works, there'll be some links in the description of this video with more information. Okay, so I've exited the presentation, and now we're looking at the problem on the CTF Learn website. As you can see, we're given three pieces of information: E, which is the public key, N, which is the product of the primes P and Q, and C, which is the ciphertext. The first step that we want to do is to find the primes p and q from n. And there are many ways to do this, but I'm just going to use an online factorization calculator. So I'll copy this value of n, paste it into this calculator, and click factor. So the calculator gave us the two primes p and q, which multiply to give n. Here's the first one, and here is the second one. Now I'm going to move to a Python notebook that I've already filled out. And before we proceed, I want to introduce two bits of the math behind RSA that we'll need to complete this problem. The first is that D, the private key, is congruent to E inverse modulo phi. So to get the private key, which we need to ultimately decode the message, we need E, which is given, and phi, which we'll need to calculate. The second is that the message M is congruent to C to the power D modulo N. So when we want to actually do the decryption, we obviously need C and N, which are given, as well as the private key D. Okay, so I've just copied and pasted the values of P and Q that we got from the factorization calculator. I'm going to remove all the spaces from them that the calculator inserted and convert them to numbers. Next, we'll calculate phi, the totient, which is just P minus 1 times Q minus 1, and we need that for getting the private key. So we can take a look at that. Here I've included the three pieces of information that the problem gave to us, N, E, and C. Finally, we're ready to get the private key. As we just learned, the private key can be found using this expression. And instead of implementing this ourselves, it's more efficient to just use a library implementation. So I install the PyCrypto package here and imported one function, the inverse function, for us. So we can use that function to get the private key D, and then we can take a look at that. Finally, we want to get the message. We'll use the second expression that I introduced right here, and the pow function, which is a built-in Python function. So the third parameter to the pow function is the modulo n. So great, we have a decoded message and we're almost done. I use the hex function now to convert the text to hex values. And the last step is to just use a hex calculator to convert those hex values into ASCII characters. And we can get rid of the 0x in front because that just denotes that the number that follows is in hex. So I'm going to take this and paste it into this hex to ASCII text converter and remove the 0x in front. So we found the flag, and that's the end of the problem. Thank you for watching, and please let the HarkerCTF team know if you have any questions.